So a pump is being used to transport toluene at 10,000 kilograms per hour from a feed tank, maintained at atmospheric pressure and 57 degrees C. Pump is located 2 meters below the liquid level in the tank, and there is 6 meters of equivalent pipe length between the tank and the pump. It has been suggested that 1-inch Schedule 40 commercial steel pipe be used for the suction line. Determine whether or not this is a suitable choice. If not, suggest methods to avoid pump cavitation. So here's our system. We've got a pump of toluene and pumping toluene, and it is located about 6 meters, 2 meters below with 6 meters equivalent pipe length. So that 6 meters of equivalent pipe length is going to take into account any head losses due to friction and the any kind of fittings. What you should realize is that this is a net positive suction head problem, and so what you're going to have to do is figure out whether or not the pressure at the inlet pump is greater than or less than the saturation pressure or the vapor pressure of the toluene. So if the pressure is close to or below the at the inlet, if the pressure is close to or below the vapor pressure, then you could get boiling and cavitation and severely damage your pump, and that would be problematic. So we've got our given information as far as the physical setup of our system. Again, remember we're dealing with Schedule 40 pipe, so the nominal diameter is different from the actual inner diameter. 10,000 kilograms per hour, so pumping a significant amount through here. And what we need to do is we need to find the properties of toluene. We need to find the vapor pressure in addition to the density and the viscosity. So I went to NIST Webbook. I think this is one of the best sites for looking up properties like this. And so we get a density, we get a viscosity, and then we have our saturation pressure that is given to us, vapor pressure given to us in a couple different units. So in doing this, what we need to do, we know that the pressure here, the pressure at the in the tank is atmospheric pressure, and they've drawn this as open. Of course, I don't think you would ever have a toluene tank open, but it's maintained at atmospheric pressure. And then we have our pump inlet here at position 2. So we're going to apply Bernoulli's equation from the tank here to the pump inlet. Note that the pump is not going to be part of our little system for applying the Bernoulli's equation. It's going to be only up to the inlet because we want to know what the pressure is at the inlet of the tank. So as we think about this, what is the velocity of the fluid in the tank? The velocity of fluid in the tank is very, very small, so we can say that it's essentially zero. Of course, we will have a velocity at the pump inlet that we need to account for. The head losses due to the fittings and the friction, those are all included in the equivalent length. We were given the equivalent length as 6 meters, so that's all included. We don't have to calculate those separately. Note that the pipe inner diameter is constant. We also were dealing with a liquid, and so it is steady incompressible flow, constant density, and constant velocity in the pipe. And so we take those assumptions and we run those through the Bernoulli equation, and this is what we get. There is no pump in our system. There is no turbine or expander, and so our Bernoulli equation ends up with this form. The pressures are different, so we keep those in. The velocities are going to be, we need to include the velocity here, but the velocity, remember, at position 1 is essentially 0. And so then we can also substitute in our expression for the head loss for flow in a pipe. And so this is our resulting equation that is now solved for P2, which is at the inlet to the pump. So we can start filling these things in. We know pressure, all right? We don't know velocity, right? We don't know the velocity in the tank. So the first thing that we're going to have to do is calculate the velocity in the pipeline, not the tank. So we know the inner diameter, we can calculate the cross-sectional area. We're given the mass flow rate, so now we can calculate the linear velocity. The linear velocity is almost 6 meters per second. If we plug that into our Reynolds number along with the properties of toluene at 57 degrees C, you see we get a Reynolds number of 3.4 times 10 to the 5th, which is fully turbulent. We can then calculate the friction factor. The friction factor in this equation, because we know the Reynolds number, it's fully turbulent. Our friction factor is 5.8 times 10 to the minus 3. And remember, this is the fanning friction factor. We're dealing with chemical engineering applications, so we'll do the fanning friction factor. And then from there, we know everything else. We know the density, linear velocity, we know everything else, so we can go ahead and we can solve for the pressure at position 2. We calculate the pressure at position 2, and this is 0.247 bar. So the pressure here is 0.247 bar. Is that higher than our vapor pressure? Yes, that is higher than our vapor pressure. And so we are kind of on the right track, right? We're kind of on the right track in that at least we aren't delivering this at a lower pressure. But what we need to do is we need to calculate that the net positive suction head allowed and compare it to the net positive suction head required for the pump before we know that this is going to be adequate. And so what does that involve? Well, that involves calculating what the net positive suction head allowed is. And so we do that, I'm saying allowed, it should be available, net positive suction head available. The net positive suction head available is equal to the P2 minus the vapor pressure, the pressure at the inlet of the pump minus the vapor pressure. So that is 0.082 bar, the net positive suction head available for our system. What we need to do then is we need to go to our pump system curves and we need to look at the NPSH-A and NPSH-R graphs. And so those system curves, they can be given to you in a number of different units. They can usually on the x-axis it's volumetric flow rate, but it could be linear velocity. And then in the on the y-axis, the head could be expressed in terms of pressure, or sometimes it isn't expressed in terms of head itself, which is remember units of length. And so what we can do then is the textbook gives you an example system curve for the pump, where they give it in terms of the linear velocity delivered by the delivered to the pump, or delivered by the pump, and the net positive suction head in pressure units. So our NPSH-A is 0.082. If we look at what is our linear velocity, our linear velocity is 5.98, let's just say 6 meters per second. So here is our 6 meters per second, and they have drawn this line, and so you can see that the net positive suction head required is 0.4 bar. Our net positive suction head required is 0.4 bar. Available is 0.8 bar. What this means is this is highly inadequate and not acceptable. NPSH-A available is smaller than NPSH-R. This is not acceptable. As your book states, for chemical processing, we generally want the NPSH-A over NPSH-R ratio to be at least 1.1 to give us a little bit of a safety factor. This NPSH-A should be at least 0.44 bar, all right, since NPSH-R is 0.4 bar. So this illustrates that even though when we calculated the pressure of at our pump inlet, our pressure was higher. Our pressure that we calculated at the pump inlet was higher than the vapor pressure, But what you got to realize is this is only at the inlet to the pump. This is not what is going on inside the pump as far as where the when you're talking about a centrifugal pump, there's another decrease in pressure because of the vane spinning and the high velocity. You are trading pressure for velocity, and so that pressure is going to decrease yet even more inside the pump, and that is what this pump performance system curve tells you what is going on inside the pump. And so this system, as it said, would not be acceptable. What we would need to do is we would need to increase the NPSH-A available. Excuse me. There are several ways that we could do this. Number one, we could decrease the temperature of the toluene. That is, make the vapor pressure a lot higher, and so that would be one way to do it. Another way we could do this is we could increase the feed pipe diameter, so the diameter of the pipe going in here, because what that does is we're trading kinetic energy for pressure energy. We're supplying the toluene at a higher pressure. Another thing we could do is we could raise the elevation of the tank. So either lower the pump or raise the elevation of the tank. Whether or not that's feasible from a physical standpoint is something else entirely. And what you'll find is a lot of cases the pumps are put into pits. Instead of building something to raise such a huge tank, which would involve quite a bit of construction and structural engineering, sometimes people would just dig a pit for the pump. But the problem is when you're pumping something like toluene, which has pretty heavy vapors, that might cause some safety issues for what's going on inside the pump. Another thing that could be done is simply increase the pressure in the tank. Increase this P1. Right now P1 is atmospheric pressure. What if you pressurize the tank? That will certainly increase the pressure at the inlet of the pump, and that will give you you would have to do it enough to where you would reach this at least 0.44 bar for your net positive suction head available. That is the solution to this problem. One of the things that I want to note is that this problem, it comes from the textbook of Turton et al. 2018. And there are a couple things in there that I want to bring up that the textbook does not take into account when they solve this problem. So this is extra, but what this in the solution to the textbook, they neglect the velocity head at the pipe inlet, and if you do that, I don't agree with that. They do that for simplicity, but the velocity head is actually significant. You've got the pressure head, you've got the elevation head, you've got the head losses, and then the velocity head. That number is not insignificant. That is basically the same as your elevation head. So I do not think that neglecting the velocity head is a good assumption, and so I would beg to differ with how the textbook solves this particular problem. Another thing that I noticed in the textbook is that their properties of toluene were a little bit different. Again, I think the NIST webbook site is, as far as I have found in the recent years, one of the more reliable sites. If we can't trust NIST, I don't know who else we can trust. But anyway, you can see that there's some pretty big differences in what for example, the density that was used, which is going to go into the Reynolds number calculation and into our pressure head calculations. So there's a big difference there. There's also a difference in the saturation pressure, in the vapor pressure. So again, be careful about the sources that you're using for your properties. Make sure that you're using good sources. Another thing that I thought was not well done by the textbook is that they were using the roughness factor in ID in SI units, and There was a little bit of a difference, not that much, but enough of a difference in the friction factor that I question what they were doing in the textbook. And this made all of these differences actually made quite a significant impact on the values that were calculated. Notice that the textbook obtained a value of NPSH-A available of 0.37 bar. What was ours? Ours was 0.082 bar. So there was a big difference. And I think the textbook had some issues in solving this problem. So anyway, be careful as you do these problems, and also be careful when you do these NPSH calculations. We're not just looking at the pressures. We have to combine that with what our actual pump is rated for, and so we need to be able to read these pump performance curves and then make our decisions based on what we've calculated, hopefully using all good assumptions and good properties.